in the image that you are watching right now. Okay, so for today's presentation, it's my turn to present, and we are going to discuss about physical modeling of fully cemented reservoirs with a geotechnical centrifuge. So let me just go through this with the pointer. Okay, so first, I want to do a land acknowledgement because all this research was conducted here. This has been the traditional lands from indigenous people, but mostly where the university is landed was the part of this land where these people use meat to discuss ideas, to have an exchange of ideas, and it's great. And I'm grateful that this land still is destined for that, to just discuss our ideas and to pass through generations. I'm going to begin for the end, which is just highlight the team that is behind the project that I'm going to show you, especially Dr. Olivesa, Dr. Gonzalo, my supervisor, Dr. Rick, and the team from the centrifuge, which is Yashao and Dimitro. So the first part of this presentation is looking for a tool. And what I'm going to try to explain you is the tool that we make and we design and how it works. So this work was intended to explain and to try to understand what is called CHOPS reservoirs. So I'm going to spend some time in what a CHOPS reservoir means, because most of you can have a kind of idea, but limited idea of what a oil reservoir could be. So here you can see Alberta, BC, Saskatchewan. Here are our deposits, sand, oil deposits, and here we have what is our heavy oil deposits or reservoirs. You can see the distribution of those reservoirs. That is the Lonsminster area. So there are reservoirs that go from a thickness of kind of 2 meters to almost 12 meters. And you have those reservoirs and a depth of almost 500 meters. I want to call your attention to this number, which is the viscosity of those fluids that are in those reservoirs. It's 25,000 centipoises. That's more than even honey. You know that even the normal honey the normal honey, that's even thicker or viscous than that honey. So that's the kind of fluid that you are trying to move from 500 meters below to the surface clearly. So right there is the challenge. So what CHOPS means is coal, heavy oil production with sand. So coal means that there is no any kind of thermal or chemical process or enhanced oil recovery. You know pretty well this equation. This is just the basic Darcy equation. When you have any process, thermal or chemical application right there where you are changing, mainly is the viscosity of the fluid. We know pretty well that heating oil just reduce the viscosity so you can produce in that way. Heavy oil is the oil that is between 100 and 10,000 centipoises. But look at the density. Here you can see the specific gravity is quite narrow. Okay, so this is oil that can be even heavier than water, and that's counterintuitive because most of people believe that all the oil is lighter than water. That's not true. That's not true when we are talking about heavy oil and extra heavy oil. Those could be even heavier than water. And some production with sand means that what these people create as a system to be able to produce that oil is induce the failure, the mechanical and the shearing failure of the rock. And then from here, the wellbore, you are extending that failure. So you are creating what they call wormholes. So those are cavities. And when you create those cavities, now what you are affecting is the permeability, because you are creating high permeable channels. Then you can produce more, because again, here in this Darcy equation, where you are increasing is this K, which is the permeability of the reservoir. here you can have a description of how the change of the oil production. This is a typical behavior for a wellbore in that Lloydminster reservoir. You have here the rates, and you can see when they begin the production of sand, there is a peak of production in the oil. And with the time, what happens is that the oil decreases, but you keep a high water rate, which means that at the end, the process is not economical. But then what happened, what explains the production with these chops? So there are gravitational forces. So you have, again, as I told you, 500 meters of rock over that the overburden of that reservoir, which means that the vertical stress is constant and is there, and you are supporting with the consolidation of the rock, you are supporting just squishing the reservoir so the oil can come out. There are also something called foamy oil. What is foamy oil? When you have a really viscous oil and you decrease the pressure on any oil, the gases trying to release from that viscous fluid. What happens is that if that fluid is extremely viscous, those little bubbles, they nuclearize, but they cannot do a continuous phase. And it's where you are watching here. You can see that here you have the oil, they decrease the pressure. And what happens is that these little bubbles, they, again, nuclearize, they are released, but they don't form a continuous phase. So if you have this in your reservoir where you are having these little bubbles that are expanding and pushing the oil out of the reservoir, and of course you have the sign influx. Here you have the wellbore. You create that failure, and when I say you create that failure, we study this in geotechnical engineering. This topic is in geotechnical engineering is because the failure of a rock is just a topic of geotechnical people, right? So you can see all the possible mechanism here. Actually, what is predominant here is a huge liquefaction of a poorly consolidated sandstone that is going through the wellbore. In other words, what I'm trying to say is if there is people that is interested in phenomena like the failure of rocks, the failure of weak rocks, or liquefaction, oil industry have spent tons of money understanding that, because that's their problem. So that's the moment where you have to expand the scope. Don't believe that the only people that study failure in rocks are civil engineers. No. And there are people, I have to say, there are industries that have more money and they have studied this because that's their business. So this is what they do, and they have studied this. These channels are called wormholes. And yeah, the idea beneath the wormholes is here you have a high permeable channel because you are producing this sand through the wellbore. So you are creating every time more extended wormholes that allows the oil to be produced. So what is post-chops? So in a post-chops, you already have your reservoir, you rate of water is that high that you cannot produce more through that. So what you are trying to do is, the main problem is there is a low recovery, so you want to recover even more oil from there. But now you have in your reservoir is not an intact reservoir, you have some wormholes right there that you create during the chops phase. And some of the recovery mechanisms, they are not effective anymore. So you have usually usually you have three options to continue with those reservoirs. Number one is just water influting, which means that you inject from a wellbore, you inject water and you push the oil to the other wellbore. That's not a good idea, because if you can see here in this sample, here you have the wormhole. So if you inject water, what the water is going to do is just go through that wormhole. It's not going to sweep any oil from there. Second option is that you do thermal EOR, enhanced oil recovery. And that's not a good idea, mainly because those reservoirs are that thin that you are going to lose a lot of heat in the surroundings formation. So not a good idea. the third idea is you do a continuous solvent injection, which is now you inject no water but a solvent, but you have the same problem, is this discontinuity. So our idea was, okay, let's do it in a cyclic way. You inject here, you close your wellbore, wait for that solvent just to soak, and now you open the wellbore and you produce by here and do that cyclically. So what you get from this option is that you are affecting, again, now you have the permeability, but you also increase the area and you reduce the viscosity with the interaction of the solvent. So you are affecting all this part of the Darcy equation so you can produce more. Now, let's talk about deformation and geomechanics. That was just the introduction. Now let's go into this. I'm going to show you here, and I highlighted some phenomena that happens in reservoirs that I'm pretty sure you can relate with phenomena in civil engineering and in geotechnical engineering. Here, you have overburden stress redistribution, which means that could be subduction. Subduction is quite similar to settlement, but in a larger scale, and in an asset that is from interest for some companies. Here you have shearing regions where there is huge dilation. Imagine the dilation that there is there, that you are producing sand. I mean, you are just disintegrated the rock and taking that rock in pieces to the surface. That's the amount of dilation that is right there. Here you have an increase, of course, an increase in the porosity. You have changes in the saturation. Now look at this, because this could be way interesting. Because in oil reservoirs, the saturation is oil, gas, and the sand saturation, which means that it's not just water. Here we are not talking about just one single phase. We are talking about a multi-phase problem. That could be interest for people that is trying to understand unsaturated zones. Unsaturated zones are kind of problematic on civil engineers, but they are quite the norm for petroleum engineers, because petroleum engineers are not interested in producing water. I mean, water is not the fluid of petroleum engineers, and they are always dealing at least with water and oil, and in sometimes water, gas, and oil. And here you have changes in permeability, you have changes in the effective stresses, and you have changes in the compressibility. So this is why we are here. You can see the redistribution. If you create a cavity, you have already here a wellbore, which is a cavity. And around the wellbore, you are creating a cavity through the liquefaction of a zone. You have clearly a redistribution of the effective stresses, the vertical, the radial, and the tangential stresses. Here you have that redistribution. And here, again, the discussion that we have about those wormholes. So this is clearly a geomechanical problem, and that's what we are trying to understand. So you can see here there are three important things. One is that there is a stress redistribution and a stress change. So if we want to have any tool, that tool must be able to replicate or at least be kind of honored with those stresses. So a tool that does not apply those stresses kind of similarly is not a good tool for this analysis. Second, you need the wormholes in the wellbore. That's what is particular in chopped reservoirs and these poorly cemented reservoirs. And third, and way important, is that you need the radial flow. Most of our experiments about flow are linear flow. What happens with linear flow is that at the end you produce sand, but it's just an action of the viscous forces. It's not an action of the mechanical. When you have that radial flow, it doesn't happen. So what are our challenges? Just emulate that drainage area, honor those stresses state, and represent those wormholes. So for emulate the drainage area around a wellbore, we are going to use a centrifuge. The centrifuge we have here at the university to honor the stresses we just design and manufacture a cell. We call it Geotechnical. And to replicate those wormholes, we use a particular technology here that is the 3D printing. I'm going to show those quickly. So geotechnical centrifuge, I'm pretty sure that most of you already know this, all the theoretical background that is behind this. So what you do is you have you have your model, the one, you have your prototype, the one that you want to model. So you create little models, and with the enhance of this gravity, so when you are in a hypergravity environment, the stresses here distribute like they are here. So you can have little models that represent huge things, and they are related, the models are related with the prototype through what we call scale rules, which are just a list of scale rules. This is not just a geotechnical thing. People use physical modeling in a lot of things. I mean, in a lot of areas. Just for mention to here you can see what is called a wind tunnel. And here, before you go and you do a huge airplane, you just do a little one, and you study the aerodynamic condition of that little airplane just in those tubes, right? And it's not because they don't have numerical analysis. No, I'm pretty sure that the people in the air industry, they have numerical analysis. It's just because when you create, there are circumstances that are difficult, extremely difficult to model through numerical analysis. Example of that is how you are going to model somebody in a bicycle, running in a bicycle through numerical analysis. Is it possible? Probably yes, but it's going to take you, I don't know, 15 years just to capture all the dynamics of a body that is moving every second. So that's when we use physical modeling. And again, it's not just one thing in geotechnical, it has been in other sciences. Here is the typical case we use physical modeling in geotechnical, and I'm pretty sure you have seen this ton of times. Here is an actual scale of a movement, a mass movement, probably a rotational slide instability. And what they do is they create just a little scale in the lab, and they just fail this. And failing this, they understand what happened, what are the mechanical mechanisms that are behind this. So that's how we use it. So what you can see is that it's an upscaling machine that allows you to do little things, go into that hypergravity and scale the behavior of that. So how is going to use in our test? We are going to have almost half a meter sample, most of half a meter sample, that when it's in 100, when it's at 1G, you can see here is the volume, but when it's at 30 Gs, the volume is just 27,000 times bigger. What that means is that what I'm telling you is that my model represents 16 meters diameter sample. So you are in the lab representing 16 meters diameter sample. That's impressive, right? Because of course we are used to these kind of conventional samples, 1.5 inches by 3 inches, or maybe in the base of the cases, 2 inches by 6 inches. That's just the normal size of a sample. Here we are representing 16 meters diameter in the lab, right? Where you have air condition, which is nice. So that's why we are using this. Now, the problem, what is the tool that we are going to use? So we designed this with the team in our team. This is just an scheme of how it is. So there are 3 main chambers here. So here in the middle, you can see the sample that we are going to use. In the middle of the whole system, there is a wellbore, because remember, this is a problem of fluid, of radial flow going through a wellbore. So you have here a wellbore that we can operate remotely, because this is going to rotate at 30 Gs. 30 Gs is 120 RPMs, which means twice per second, you are going to have a system whose weight is kind of 500 kilograms, just rotating twice per second. So clearly you cannot go down and open a valve. So we create a system to open this wellbore remotely that is in the middle. Here in the top, there is a membrane that is this membrane that you can see. Here you can see a ruler. I put a ruler in most of the pictures just for your reference. like to see the dimension of how big this is. And here in the top, you have this membrane. So what we do is we inject nitrogen here to push the sample. That creates the vertical stress. And in the horizontal, we have this system. These are just one piston. So you inject fluid and the fluid push this stress actuator against the sample. And if you see, there are 8 of them around the sample. So in that way, you create the horizontal anisotropy. Now you have 2 independent systems in which you can create vertical stress and you can create horizontal stresses in a sample that in the middle have a wellbore that you can open remotely. And finally, here in the lower chamber, is just a sand trap. So the sand and fluid that comes here from the sample, you trap here the sand and the fluids go out. Just to mention that here in the bottom, that is this plate, you have the space for some pressure transducer or some devices that, some sensors that you wanna apply. So let's see, I guess I already explained you how those stress actuator works. Let's see how this wellbore opens. So once you apply a pressure, there are 2. So the wellbore is closed during the saturation, and during most of the time when you want to produce, you just open and you align an inner wellbore with an external wellbore. You align the holes and now you can produce when you want to produce. That's why it's important to have that system, because you want to control the moment where you want to produce, when you are ready in your test and you say, I want to produce this moment. So you align those, and aligning those remotely again, you can produce. Here you have a view. I like this view because here in the middle, this is the wellbore, okay? And here you have the 8 stress actuators. Now, what is important to mention is, imagine that you want to apply also horizontal anisotropy. I mean that you want to apply sigma 2 different from sigma 3, right? You can connect this one, this one, this one, and this one to sigma 2, and this one, this one, this one, and this one to sigma 3. We agree on that. Or even more, if you want to be even more precise, you can try to apply the sigma that is at 45 degrees. You can calculate that with Kirch equation and apply that here, the maximum horizontal, here the minimum horizontal, and here the stress that is at those 45 degrees that you can calculate using Kirch. So this is the potential. Again, now, until here, where I have shown you is that you are able, in a lab where there is air condition, again, to be able to emulate a drainage area of 16 meters around a wellbore, where you can apply vertical stresses and horizontal anisotropy. Again, just in the comfy space of a lab. Now let's talk about the sample that is going to be right there in that setup. So here is the wellbore, the space for the wellbore. Here are the wormholes that we talked at the beginning. So these are no solid. They were kind of empty. I mean, what they have inside was just loose sand that allows the sand to move out. But the rest of the sample is a solid rock. What we try to use here is a 3D printed technology. And why is important 3D printed rock technology here? Because that way you can control the design of these wormholes. So you control the initial stage of your experiment, right? Here you have the properties and the spaces for the stress actuators. As you can see, the sample is almost 0.5 meter of diameter. Already it's a huge sample. There are few samples that are 0.5 meter diameter and 15 centimeters tall. So that's already a huge sample. How the 3D printing works. So you do your digital design, you go to a slicer, so it just tell the machine how to do, and here comes the print. So for the print, you can see he's applying a chemical, right? Where the zone that you want the printer is going. This white thing is just sand, it's just silica. And here comes another layer of clean sand. These go back, and now the next layer of the printing comes. I mean, the head of the printer comes and print the next layer. So printing layer by layer, you are constructing a geometry, right? A 3D sample. Here you go, after we do this, we do a thermal curing, and after that, just clean and you have the sample. So let me show you here something important. When we were printing, this was, again, this was key because here you can see the space of clean sand that is dedicated to those wormholes, right? So here you have the space for the wellbore, and here you have the space for the wormholes. This is just an example. Here you can see the normal sample. This is the normal samples that people use all the time. Is just this little one compared with our sample. And again, our sample is going to scaling up 30 times their volume. Okay, so that's what we are talking about. Here you can see the sample inside the cell. So here you can see the experimental procedure we follow. First, we saturate with that oil. That oil means that there is no gas in that oil. We apply the stress anisotropy, and after that, we displace with that light oil, which means that there are little bubbles that you can see in that oil. Those bubbles are from CO2. So what we did was saturate canola oil with CO2 and apply right there. Here, these bubbles is quite similar what happens when you open a Diet Coke or any soda, that you see those little bubbles coming out. Okay, here is the same. It's just that they are not going that fast because the canola oil is more viscous. So it takes more time. And this happens at 1 G. After that, we spin at 30 Gs. Again, 30 Gs is 120 RPMs. So twice per second, this is going to rotate in a centrifuge that is a beam centrifuge that is here at the university, 2 meters arm, and you are spinning 400 kilograms in that twice per second. Okay, before that, we did what people here likes too much, which is do numerical modeling. So we did a numerical modeling just to try to realize what was our expectations in terms of shearing and in terms of deformations. So you can see how they are changing. Again, we did this. There are a lot of factors that are not included here because what we did this not to emulate, but just to know what is going to happen before our test. Here, so let's see on a spinning stage. Again, here our samples, we have sensors here in the green spots. We have sensors. So we have sensors beneath the sample, and you can see those sensors here as a red dots. They are here, and externally here there are the accumulators. So remember, the fluid is coming here through the wellbore. Here the sand is retained, and the fluid is coming out to these 4 accumulators, external accumulators. So let's see. It's going to rotate. So it begins slow. And at some point, it's going to be completely horizontal. So once you open the wellbore, the fluid is coming out, and you can follow here. Here you can see we have a pressure transducer, okay, to follow this column of fluid. And of course, this last video was taking 1 seat stops, clearly, right? So here, what you are going to have at the end of this is a reading of stresses within the sample, a reading of the stresses within the sample through all the process, and you are going to have also the production that happens during all that process. So let's see that. So you can see here when the gravity increases, now we open here the wellbore, right? So the pressure within the sample begins to decrease. Here we did a technical stop to see if there was no leaking. There was no leaking because you can see the pressure was constant during that time. We increase again the gravity, and we open again, and you can see how the pressure decreases in all the sensors that you have in the base of your sample, okay? So those pressure transducers are these pressure transducers that are here in the bottom of the sample. And you can see how the pressure decreases as a result of the production in that drainage area. So what we did after that is, remember, we have also pressure transducer in the accumulators. So we follow that pressure. Of course, you have the pressure, but we also have images of that. So what we did was just treat those images, and knowing the height of those, you can easily calculate the hydrostatic pressure at 30 Gs. And we compare both of them, and that difference is this difference. So this shadow that you see here is the difference between the pressure that we measure with the pressure transducer and the measure that we deduce through those videos and the hydrostatic. Here, what you have is kind of the same. Here what you see is the pressure against the flow rate in those external accumulators where the flow goes. This is a technique, way interesting technique that I recommend people that is not familiar with that go into that. Petroleum engineers never have access to the reservoir because the reservoir is 500 meters below or farther, right? So what they do is they try to understand the reservoir, just measuring how the pressure change through the time and when they close the wellbore. If you see our experiments, what you have is that drainage area. That's called well testing, and it's based in a lot of equations. This is the equation we use. So thanks God that you are graduate students. If you put this in a logarithmical paper, what you have is the initial pressure, that's a constant. This is a constant. All of here is a constant. And if you put this in a logarithmical paper, the only thing that is going to change is this part. So what you have is a line, right? You have here the slope of the line, and here you have the variable with the time. And what is great about this is that if you put that gives you a line, and from that slope, you can calculate the permeability of a reservoir that you have maybe 1 or 2 kilometers below the surface. So you were able to calculate the permeability of that just based on the readings of the pressure in your wellbore. And we did that. What you can see here is we calculate the permeability just based on the theoretical and give you a range of permeability. We calculate that as a range in our case, and it gives us a number that is pretty close to the number of the real sample. And also, we were able to determine that here in the early time, middle time, and late time, in the middle time, here is behaving like a linear behavior. This means this is an logarithmic. This means that this applies, which means that you have radial flow. So this is the way you can deduce and be sure that you have radial flow, not just thinking that you believe, just comprobating through equations that if this is linear in the middle time, is because you have radial flow. And you can see it here. This is what is called a derivative presentation. And this change here is indicative of what they call a double porosity system. And that double porosity system happened because, if you remember, the wormholes have a different permeability and a different porosity than the rest of the matrix. So in this way, we were able to confirm that the boundaries and the flow pattern that we were expecting from our experiment was correct. We finished the test and we opened, and what you can see are some cracks. Most of them actually in the front of the stress actuators, as expected, and as was predicted by the simulation. Okay, so you can see those cracks, which could be for interest of anyone in geomechanics. Here you can see previous work done in centrifuge that they don't apply horizontal stresses, and they found always this cavity of sand. We didn't find that. So the question is why we didn't find that cavity. You can see this setup doesn't have that horizontal stresses, and they found a cavity. So why? Mainly, if you try to understand that way, you are where you are going to face is that difference between the resistance of the material against the dragging forces. And so the conclusion is simple, is maybe our material was too tough for that. So let's try to replicate a poorly cemented reservoir. How? You remember that during the printer, there was a heat print, the head of the printer was applying a chemical. That chemical is called a binder, which means the link between one grain here and the other grain. So if you reduce that percentage, what you have is a softer material. So for you, just to realize that, I took 2 samples. And try to. So you will touch on that. The big one, if you try to take grains from the big one, it's tough. If you try from the little one, every grain is right there. And it's because one have 20% of saturation of binder. So you can see here the image with 20%, you see a lot of links between the grains. When it's 10%, less links, right? So that's clear. When you reduce the binder saturation, you reduce the UCS, and you can feel it, right? So what we said is, okay, let's go. The maximum that our group was printing was 10%. So let's go into a new material that is going to be 5%, just half of what was done. And at the beginning, we find some challenges printing a little low material, because when it's little low bindering, so there is a lot of displacement. And after some tries, you can see here, you have now a sample that is stable and that is correct in shape. So now we have a material. Now let's see how it compares with normal samples. So, I mean, with normal reservoirs. So here you have the little sample that we are going to test, typical UCS test, recording axial and radial, in situ axial and radial deformation strains. You can see there is good repetitivity in the 5 samples that we use, and you get a really low, if you see this is just 2 megapascal of UCS, that's really low, but it's quite similar. You're going to see quite similar. This is our material to those poorly cemented reservoirs here in Alberta. Here you have Lloydminster, here you have McMurray, Cold Lake. They are here in this range. This is UCS against your modulus, and you can see that here is our sample. So now we have a sample that, at least in the elastic behavior, behaves quite closely to those reservoirs. Here we conduct just simple triaxial tests. We found really close behavior to those poorly cemented material, but I want to call your attention here in the failure mode. If you see how our sample failed, what happened is a huge dilation. I mean, we put at the beginning of the test a sample, like a normal sample, and when you obtain after the triaxial test just at 3 MPa of confining stress, is just a complete remolded sample. So this is quite the behavior also on failure that we were looking for. There is a question which is quite valid, is, okay, maybe when we increase the layers, you remember that this go layer by layer, there was no good distribution of the binder. So to know that, we run a CT scan, and we can confirm that the binder is completely throughout the sample. So it was good distribution. This is one that I really like, because I haven't seen a lot of works about creep behavior in most of materials. And here you can see that the creep, it looks like it's changing. Actually, it's not changing that much if you see the range of the change, right? So what you get here is a material that during the test is going to behave with few creep. That's good for the test purposes. Here you have hydraulic properties, good porosity to water and to oil, quite similar. So you have an average of 45% of porosity, which is as a porosity quite high regarding the natural reservoirs, but in terms of permeability, hits just in that 1.7 darcies of permeability, which is the range for those natural Lone Mister and Cold Lake reservoirs. Here you have the description of that porosity. And here you have, for those of you that are familiar with the test, if you are calculating pore pressure and you increase the stresses, you can calculate the B parameter of a skeleton, right? So what we get is a rock that has an skeleton parameter of 0.7, which kind of correspond with those poorly cemented reservoirs. So main remark here at the end of my work, we were able to create a brand new tool from zero that is able to emulate the drainage area around a wellbore that is capable to manage multi-phase flow because we created for that, and that is able to create a stress anisotropy between the vertical and the horizontal, and you can even use different horizontal setup to replicate. And plus, and additional to that, we were able to create that brand new material with low boundary condition and characterized. We have the UCS, we have the Young modulus, the Poisson ratio, we have the triaxial behavior, the failure behavior, the creep behavior. We also have a CT scan that allow us to know how is the distribution of those. And we have parameters that are interesting, like the B parameter of a skeleton. So at the end, when you get that brand new tool that we create plus that material, at the end, what you are able to do is that physical modeling of a poorly cemented reservoir. So that's the result of my work and the work of my team that is all part of the reservoir geomechanical research group in 3 of his facilities: GeoServe, which is the centrifuge; GeoPrint, which is the printing; and GeoRef, which is the one where we do all the UCS and triaxial tests and so on. So again, this is the main remark. And some other remarks is that, as I told you, we were able to have a multi-phase centrifuge cell, which is one in its kind in the world. There is no something like that in the world. There is no in the world something that can apply also triaxial stresses in a centrifuge when it's rotating. We were able to manufacture identical chop samples thanks to the printing, because if you print one sample, you can print 5, right? And they are statistically the same. So that's actually a good note for you, that if you have one of the problems, the challenges that we face when natural samples is that they are, even if they are taken from the same outcrop, they are different, right? And we know that they are different. We assume that they are equal, but they are different. Here you have samples that are identical, are statistically the same sample. So that gives you the problem of the heterogeneity out of the equation. Is that true in the real life? That's not true. But is that good for research? That's so good for research, because then your conclusions delayed a huge variable. Again, that's no real life, but for research, it's a step, right? We were able to do this direct upscaling. Again, remember that we were able to emulate that drainage area, 16 meters, a more realistic boundary condition with those stress anisotropy conditions and applications. And we have a partial representation of that poorly cemented reservoir, strong dilation and loss of integrity, which matches with what happened in the reservoir, and minimal secondary creep, and is going into the range of the poorly cemented reservoir in terms of porosity and permeability. So this is just thank you. This is the end. And if you have any questions, just let me know. Thank you, thank you. Any question? I have no idea. I'm the one who print those. I don't know. I guess for us, it's quite cheap because we already have a printer. But if somebody goes through all of that, what I know is that our group prints samples for other groups here, here for even for pedagogical purposes, for groups here, and also for groups in other places. Yeah. But I guess it depends what is the purpose of the sample, because when it's for industrial partners, it could be quite more expensive for them. But in any case, they are cheaper than drill a wellbore. And not, it's not just drill the wellbore, it's that taking samples for a wellbore, a deep wellbore, I mean, petroleum wellbores. Imagine 1 kilometer. A petroleum wellbore is easily 1 kilometer long or longer. That means you have to take all the crew right there and try to take those samples is way, way, way expensive. And at the end, you are not going to take those samples, somebody do the coring, and they are not going to allow you to do a destructive test in a sample that could cost $2 million. You know, I mean, all the people is going to, first the geological team is going to do all in that sample. After that geological team do all the petrophysical team is going to do tests that are not, because how you can explain somebody that you are going to spend $2 million taking a sample to destroy it in a triaxial test? Quite difficult to explain, you know, quite difficult to explain. So yeah, they are, I don't know how much they are. What I know is that they are good resource to replicate, and that they are cheaper than do a wellbore. Yeah. Oh, there is a ruler. Good question. Here there is a ruler. Let me go. Oh my goodness. Do you remember? Here. Let me see if I'm able to play this. Okay, so you are printing, right? You have here, this white thing is just silica, white silica, right? Here you are printing your sample. And here, when the next layer of silica comes, here there is a ruler, just at the front. He's moving, you see? Moving. That's the way you consolidate. You increase the density of this, just doing mechanical ruling over the thing. Yeah. Does it make sense? Yeah. Yeah. So every layer, of course, your ruler is working. Yeah. Now, we must say, just for conceptual, for people that like to be purely conceptual, that consolidation in rocks is no closed term. Consolidation is a term that usually people that is more pure use just for soils, right? Because in the rock, the increased good part of the consolidation itself is given just by the bondings between the grains, which is something that you don't have in the soil. In the soil, part of that strength is just given because all that compaction, I mean, the redistribution, when you squeeze the water out, you increase the density and the grains accommodate themselves. In a rock, in a sedimentary rock, part of that integrity is just, most of that integrity is just given by the cementation between grains. But yeah, that's the answer. Thanks to that ruler, basically. Yeah. Any other question? Yeah. Yeah. Just give me a moment because it takes. It's because it goes like through the videos. I don't like to creep here. Creep. Beautiful. Yeah, for sure. So for those of you online or here that are no familiar how a creep test work, there are two ways to understand creeps. One is in an odometer. So you place in an odometer your sample or your rock, and you apply a force and you wait forever. So there is always something that is initial creep here that happens, they call primary or initial creep. here happens at the very beginning. So what you can see here is the deformation, the axial strain against the rate of that strain, right? So at the beginning, that rate is too high. I also calculate for, because it's easier for people to see here, the mobile average of that strain, okay? Because this rate, I mean, the way the strain is changing is kind of messy. I mean, you can see a trending, but it's kind of messy. So I calculate a mobile average. But here, after some time, begins what they call the secondary creep, which is like a plateau, you know, like a steady state in which the strain doesn't change too much. And you can see that because the strain doesn't change too much, and the rate of the strain is kind of constant. Again, here it looks crazy. But actually, if you plot this, look at the number, right? If you plot this between 0 and 1, this is aligned, absolutely aligned. There's no change. Even if you plot this between 0 and 0.1, this is aligned. So there are two ways. That way with an odometer, the other way is you do what they call an isotropic creep test. An isotropic creep test, you take your sample into a triaxial test, into a cell, you apply an isotropical condition and you wait. Of course, you are monitoring, you have inside your cell, you have LVDTs or you have LPs. We did this in one of those as an isotropic test, and you just wait. Yeah, you apply that test and you wait. So again, the way to read this is here you have the initial primary creep and here you have the secondary creep. What you are expecting is that the secondary creep behave like a steady state. You confirm that having this rate near to 0. If you see here the strain is near to 0, because here is not changing. And there is something called a third state creep, in which this creep begins to increase. So there is a initial deformation, no deformation, a little deformation during the time, little, and there is a moment the sample cannot stand more than isotropic behavior and begin to again. So what you will have, what I'm trying to say is, let me explain with the pen. Here, it begins to support, and it begins to increase the strain. So here, you're going to see again this to increase, right? This strain rate, and poof, until failure, right? That takes time. When I talk about time, in our lab, there are people that has been doing creep tests for months, like 6 months. It takes time. That was not our case. Like, we were not interested on that part. We were just interested on be sure that that material during the test is not going to have any kind of extreme creep behavior, right? So that's why we just do for 500 minutes. 500 minutes is something like 10 hours, 9 hours. Let's say 9 hours. So like almost any test is going to end in 9 hours. Yeah. Any other question? Okay, thank you very much. Hopefully see you all next week, that we are going to have a presentation from one of our professors here, Professor Gonzalo, hopefully. Yeah. So yeah, see you next week and see you in the retaining wall competition.